This meeting is being recorded. I don't know if you guys heard that. All right. So I need screen share. I need to go to OneNote. All right, and aptly titled. We're gonna hopefully today get to some polyprotic titrations here. First, I did want to take that little backtrack. You guys drew a little titration curve there for the HF as your homework with some, I think, lithium hydroxide. Awkward silence probably means yes, and no one wants to talk.
It's yes.
All right. Wow. Since I've been watching the American Idol stuff, it's almost like you sound like Luke Bryan. It's a yes for me. So did anybody have questions? Now, I actually gave you guys bigger volumes than what I had. My original prompt was only 30 mils. So I hope the numbers scaled accordingly. Your endpoint, what was your endpoint?
Right. 150 mils.
150. I would say that's probably right, which means your halfway would be what, 75?
75, yeah.
Okay. What did you guys get as your initial pH then?
1.93.
Mm-hmm.
Okay, that's what I had. And your midpoint?
3.45.
Right, so those would be pretty easy there. And your endpoint, I think, will be slightly different from mine. What did you get as an endpoint?
8.44.
Oh,
yeah.
Interestingly, it stayed exactly the same, but I guess that makes sense because even though I scaled everything up volume-wise, everything else scaled accordingly. So, yeah, so we had all that. And I assume you guys had no problem getting some of the points in between. Did any of them give you any trouble not following a trend?
No.
Okay. Did anybody have questions about that problem? And did I make you go over? I forget.
No.
No, I didn't. Okay. Okay. Well, if no one actually had a question about that, I guess I want to do one more here of the what is going on, because I think that is that's still something that we need to do a little bit of work on. So what I want to do is go ahead and try to give you guys some ingredients and ask you what is going on. So let's see. More of what is going on. So what if I give you some sodium hydroxide and acetic acid, HAC. Let's see, since I actually know your names. Patrick, what are my ingredients?
AC minus plus H2O goes to HAC and OH minus.
Yeah, so those are our two ingredients. So in the end, this would be AC minus plus H2O, goes back and forth to make HAC and OH minus. Remember, we are making sure that the charge is balanced. We have a negative charge on the left and a negative charge on the right, so that charge will be maintained. All right, how about some NH4Cl with HCl. Is there a way to just get a bunch of lists here? Oh man, I just want the list. Oh, I can maybe go to participants. Hold on. Let me go back into this. Participants. There we go. Can I drag this? There we go. All right. Alexia, what are my ingredients? if you decline to stay, don't just sit there. Just open up and say no. All right, Kimchi, I know you'll talk to me. What are my ingredients?
It's NH4 and H.
And H. And the equation that would have NH4s and H's
Yes. So
would
the
be what?
NH4 goes down into H and NH3 or NH4 plus. Sorry.
Yeah. Goes down to NH3 and H plus. Doesn't matter the order. Now, keep in mind, you know, just for full on, remember that's actually NH4. NH4. Wait. I don't want to do that. I don't want to do that. Don't want to confuse the issue.
Wait, equilibrium arrows, right?
Oh yeah, that should be an equilibrium arrow there. Thank you. Let's see. What if I have NH3 and some KOH? Chef, what are my ingredients?
NH3 and OH.
OH. Can you guys see my cursor when I hover?
Say it again?
Can you see my little dot cursor when I hover over the top of it?
No.
No.
Oh, good. Because I was like, oh my gosh, I'm like totally telling them the answers. I'm like hovering and my pen's like, you want right here? You want right here? I'm like, oh, giving them the answer. All right, so Chef, what equation are we going to be writing here? Acid or base?
It's a base.
Okay. So what would we do?
I don't know. Something plus H2O.
Okay. Something plus H2O goes back and forth to make something plus
OH.
OH minus. Okay. So now that NH3's got to go on one of those sides. Is NH3 an acid or a base?
A base.
All right, so we already have a base on the right, so we might as well put that base on the left to then make its conjugate acid.
Got it.
Notice we have a plus and a minus on the right, and we have 0 on the left, so we have that. That one's slightly tricky. You guys seem to be doing okay. How about some sodium acetate and HCl. I'm going to throw that one to, whoa, stop that. I don't care about it now. Stop it. I'm going to throw that one to Lion Lee. What are my ingredients?
Your ingredients are going to be HAC goes to make. Oh, hell.
No hell. You do know you're being recorded. So watch your language, man. No. You're giving me the equation. I want my ingredients first. Then you can give me the equation.
Your ingredients are going to be AC minus, H plus.
All right. So go ahead and give it to me then.
HAC goes back and forth to make H plus and AC minus.
Okay. Oh man. What should I do next? Let's step this up a notch. Soto, you look really quiet and concerned over there. How about this? I want to do some. I don't know if you guys can hear the kids screaming in the background. Might be a little quiet. All right. Soto, what are my ingredients? Or tell me no. Or Gherkin, save him.
Oh, I think he wrote it in the chat.
Oh, you know what? Oh yeah. So here's the deal, guys. I can't actually have everything up to see it. So I tried yesterday having my desktop up so I could see chat windows and also see this. But it was kind of hurting my head to bend over to write so much. So I don't have all of that up. So voices, I guess, please. That way everyone can sort of hear any questions or hear the responses. And if you don't want your voice on here, that's totally fine. Just say no and I'll stop calling on you. I'll assume that means no. I saw more show up. What was that? Is that more?
Dallas said not everybody has microphones.
Okay, that's cool. All right, well then, I will assume that Soto said my ingredients are an H bens, a bens minus, and an H plus.
Yeah.
So with that, I'll also assume he said, that's easy. You gave me every ingredient for an H bens, breaking apart to be H plus and bens minus. Wait, does Dallas have a microphone?
Doesn't sound like it.
Just kidding, Dallas. We miss your dulcet tones. Now, I do want to point out with this one, we do have all of the ingredients. So what we want to do is choose the best and easiest one. And always the easiest one is something breaking apart, meaning the H bens breaking apart. You wouldn't want to try to go and make some sort of base out of this for a couple of reasons. One, we have the H plus sitting up there. And two, it's more complicated than just make this thing blow up. So, oh, you know what? You know what I might do real quick? Just for this, let me stop sharing for a second, I think. Hold on. And why don't I just get a quick little, no. Oh, I do stop share up there. There we go. Let me do a quick little hands. I'll just write down who can actually talk to me, and not to get rid of anyone, but that way I don't be like, hey, why are you doing this? So Kimchi, Alan, Mang, Gherkin. 4 of you can talk to me. Okay, Boudica, Rio and Johnson. All right, so those take your hand down if you don't want me to talk to you.
I don't know where the hands are.
Yeah.
Oh, Lion.
Wait, can you hear me?
Yeah.
Oh, okay.
Hands are if you go to participants, to be able to raise your hand.
All right, cool. Thank you.
She's not a participant? Oh, there she is. Oh, okay. And then Ben and Chef.
Oh, crap. There we go.
Oh, and Issa, man. And Alexia. All right. Okay, cool. So that gives me a good list from which to choose to sort of say, help me. So I want to make this as interactive as possible. Otherwise, it's kind of boring. I could just make these vignettes and just sit at home like, I'm not gonna go there. All right, how about we have HAC plus NaAC plus NaOH. Johnson, what are my ingredients?
Your ingredients are HAC, AC, and OH minus.
Okay, what's the simplest one you can make here? The acid or the base?
The acid.
The acid or the base?
Oh, the base.
Yeah, and keep in mind, especially when we get multiple things in here, one of them may accidentally tell you exactly what's going on. In the top one, we had HCl. We obviously have to do the acid. Here, I threw the base in there, so obvious answer is obvious. We need to do the base version. while we do have we could try to write the acidic version, that OH would kill everything and therefore just ruin our day. So,
Okay.
Kyra, go ahead and give it to me. What would it be?
AC minus plus H2O goes back and forth to make HAC plus OH minus.
I like it. I like it. Okay. And keep in mind, I think this is probably obvious, but in the, I'm gonna scroll up there. What is the governing equilibrium for this AC minus? That's going to be a K. B. The next one, the NH4, is governed by a Ka, because we're making the H plus. The next one with the OH minus is a Kb. Then we're going back to a Ka, and a Ka, and then a Kb. Always making sure that we know which one we're looking at as we get these things. Okay. Any questions on that portion?
Yeah, this is Chad. I just had a question on, is there like a reference in our book or somewhere that we can look to understand that governing, you know, just like you talked about, whether it's Ka or Kb. I mean, I would have picked the AC over the OH, but I guess that was obviously an ignorance. So
Which one? The last one?
yeah, I mean, OH is a stronger base, is why you chose that, correct?
Well, actually, I chose it because it is taking the form of a base equation.
Okay.
Okay. So what? And the nice telltale of that is I do have this OH over here that is telling me that it's a base reaction. So I have that. What am I doing now? I wanted that color. But the fact that I actually started out with this AC minus, which is a base in and of itself, tells me that on the other side, I will make the OH minus. Keep in mind that the acetate is I mean, it is a base insofar as that it will generate OH minus on the back end. Right, that's the one that's really going to be doing the lion's share of acting like a base, but it is coming from the AC minus. So oftentimes if you're trying to figure out, is it a Ka or a Kb, it might for you be more useful to see, okay, what am I spitting out on the other side? Is it an H plus for a Ka, or is it an OH minus for a Kb? It might be easier for you to look to the right side.
Okay. Yeah.
Does that make sense? A little?
Yes. Yeah. No, definitely looking at the products is definitely where they can determine the equilibrium K or Kb. But I guess just trying to understand that OH is going to be on the right side with AC on the left is where I'm.
Yeah, I think I see your question, and the question basically comes in like, I'm so used to looking at my my reactant side to see what is going on. Like when we talked about types of reactions in Chem 120 and things like that, we're always looking at the left-hand side to say, oh, what is it? And this time, actually, our biggest clue might come from the right-hand side, which is odd to think, but there it is. And Kimchi, tell me how you really feel about that yawn. It was big enough to take over the mic.
Oh my God, did you hear that?
That's why I like this class. We have fun. All right. So, oops. Well, I don't care. Let's just get a line there. Okay, let's do this. Show of hands. So take down your hands, everyone, unless I can do it. Okay, Boudica, Chad. Show of hands. Do we want to do one more monoprotic acid with an overtitration, or, drum roll please, skip to polyprotics? Show of hands for a monoprotic. Show of hands for skip to the end. Oh, wait. Were those all for the mono? Oh, skip to the poly? Holy crap. All right. I guess that's everyone. Oh man, you guys, either you are fooling me or you guys are finally getting this. All right. Skip to the end. My only friend, the end. All right. Let's talk about polyprotics. So, ooh. Oh, bummer. It didn't like my poly. All right. So polyprotic acids, as the name implies, we are now dealing with more than one proton or more than one H. So this is more than one H plus. Coming on. Of course, we're talking about things that are like H2SO4, H3PO4, H3CID, etc. Now, I should probably put H2SO4 in parentheses because it's a strong acid, so we won't actually be doing anything with it. Just showing you that it is a polyprotic. I'm going to draw something. This is going to be glorious. Ready? Shapes. Bam. Because I know how to do this now. Is that going to be big enough? Let me get a little bit bigger. Oh, nice. All right. So this is going to be the general curve of a polyprotic. And we're going to come back and we are going to put all these things here. Actually, we could probably put a lot of them here. But let me just start with this. On the one side, we have pH, and on the bottom, we have the volume of base that we added. Now, in general, this curve will look something, ooh, this is gonna be fun if I can do this here. I'm just gonna do a diprotic, so 2. So let me just, I wanna give myself a reference point. Let me start. Oh, probably should have moved all that down. I can do that. Oh gosh, if this works, oops. If this works, I'm going to really start to like this one note thing. Maybe I'll do everything in one note. I'll just stand there and move that down. Oh my goodness, that is glorious. All right. All right, so let's take a look at what I've done here on this plot. I've drawn essentially what looks like 2 monoprotics stacked one after the other. Can you guys see that? So I have what look to be like 2 monoprotics stacked right after one another. Now, when I did the general form of a monoprotic, I put it up there, and it should be no surprise that all I did was take another monoprotic and stick it after it. The general form is conserved. As we look at any H coming off, the trend will be the same. The one thing that might differ is either the length of that buffer region or even its slope. Some of them change rather quickly depending upon their strength and the total amount of volume. Others are very flat for the same reasons. Now, if we take a look, we actually have a couple of points that we can already put on here because we've already been doing them. And I proved it to you the last time. The first one would be the initial point right here. This initial point right here. What governs, what equation did I say would govern determining that initial point? You guys remember? Where's that? Oh, I guess I should have figured out how many people could write over the top. And how did I make that happen again anyway? Oh, you can go into the annotate, right? You guys can do that yourselves?
Yeah, we have to do it.
Oh, okay. Well, oh, hey, someone's writing on there.
Wait, I don't know how to do that.
Boudica, tell Loban how to do it.
So at the top, you should see like the green where it says you're viewing professor screen. Then there's a view options that you click down, and then there's annotate.
Ooh, someone's writing HA.
Oh.
Back and forth to make H plus and A minus, right? Who's writing that? Dallas, okay. So Dallas doesn't have a mic. Okay, so Dallas is not wrong that he's done the monoprotic there at the other end. What I was going for is if we were to actually figure out the pH of that situation over there. Go ahead and take that away, Dallas. Thank you. I was hoping that someone would remember that this point is x squared over A minus X equals Ka. Now I'm actually going to do a Ka1. And the reason why I'm going to do this is if this is a diprotic, this should be some sort of generic form of H2A, goes back and forth to make H plus and HA minus, governed by a Ka1. That will be the first H that we do. The second H will be HA minus, going back and forth to give us H plus and A with a 2 minus charge. That will have its own equilibrium Ka2. So that's the reason why I'm annotating that x squared over A minus X equals Ka1. Does anyone not remember how I got there? Okay. That being said, there's a couple of other spots here that we could make some inferences here of, and that is the endpoint up here. How would we figure out the pH on that one? I'll give you a hint. It starts with x squared.
X squared.
That one's with the base.
Right. That's x squared over B minus X. And that's going to equal a K B. Now, we're going to go the second one because when we look at our actual conjugate base here, it is from that guy, which is governed by the Ka2, but since we're going to be talking about the base, it'll be Kb2. There are a couple other spots in here that we should intuitively be able to do. I'll give you a hint. One of them is right there, and the other is right here.
The halfway point?
Yep. So in the halfway point, Rio, give me that first one. What's the equation for it? Or Isa?
pH. Oh no, pH is pKa.
Be specific. If
Oh,
I wish I could
pKa1.
do this, I wish I could like cover up my screen so you could see. I'm covering up the right half of the plot to show it as a monoprotic. If this were just a monoprotic up to the first point, that pH of pH equals pKa1, which means, give me the other one. pH equals?
pKa2.
That's right. Ooh. Now I'm going to go ahead and label these as region 1 and region 2. Okay. Other points that we should hopefully intuitively be able to get. Let's see. How about this point right here in purple? on the x-axis, what might that represent? In fact, let me just go ahead and put a big line here. These two purple lines, what might that be all about?
How much base is added?
How much base is added to what? To what end? Oh, shoot. I gave you the answer.
The,
Starts with the end, ends in point. Say it.
To take away the next H.
Yes. So the first one is to take away the first. The second one is to take away the second. So this guy right here, this is the end point volume. And in this, I would say that's the first endpoint, which means this guy right here is the second endpoint volume. Now, how do we get that endpoint volume?
Which one?
Well, the first one, you don't know how to do the second one yet until I point out that you actually do know how to do it. How do we get the endpoint volume?
The M1V1?
Yep, M1V1 equals M2V2. Now, how do we get the second endpoint volume then?
Can it also be M1V1?
Sort of. It is, but you don't have to be that clever. Or I should say you can be cleverer. Notice how I drew it. I drew it very symmetrically or very methodically.
So you just double it?
That's right. If it took, say, 100 mils to get rid of the first H, why wouldn't it take 100 mils to get rid of the second H? It's just an H. So when you look at the second or the second endpoint volume, it is just double the first.
I have a question.
Oh, yes, Kimchi.
So it's the same, but what does that have to do with like how the KAs are different magnitudes?
Well, keep in mind that we will see that everything has its own Ka, right?
Right.
Now, we've been talking about mostly our Kas being in the realm of 10 to the negative 5s or 4s or 6s, but others will have them in the realm of 8, 9, and 10. If you were to take the pH based on that pKa, you would clearly see that it is going to raise that curve up.
Mm-hmm.
And so, for instance, if you are going all the way to a full neutralization of something like phosphoric acid, you'll find out that the PO4 minus is pretty darn basic. That's the reason why they use it as cleaning additives for detergents and things, is because bases like to attack organic material. And let's face it, you're cleaning all the organic material off your clothes. And so they're putting that in there to really sort of, beef up your detergents.
Okay.
There's one more spot in here that I think we can label, and we might be able to do so intuitively. And that is this guy, right? Ooh, do I have another color? Now I'll just do this one again. Right there. Check that out. So that is the end point of the first H. And if I were to conjecture, what do you think that would be for getting its pH? How would I get that pH? Just take a stab. What would you like to do? Intuitive stab. Ben.
I'm thinking you can take the difference between pKa1 and pKa2.
Difference, or I like the difference.
Average, maybe?
Average. So, and we'll prove this here in a second. That'll be pKa1 plus pKa2 divided by 2. And we're going to go ahead and prove that here in just a second. But I just want to point out that our intuition here is going to serve us well in doing most of these problems. This problem is really no more difficult than a monoprotic, and you can be damn sure I'm going to give you a polyprotic on your exam. I'm just going to point that out. I do want to point out a couple of other things in here for the region 1. As I sort of pointed out down here below, I'm going to go here and annotate this. That's region 1, and this is region 2 for the governing equations. So when we go through and we start looking at what is going on in each of the realms, keep in mind that region 1 is governed by the top equation of the H2A breaking apart, and the region 2 is governed by HA breaking apart. No more the rest of it.
Bless you.
Thank you.
Now, all right. Let's see. I wanted to do something here. Why don't I go ahead and prove here something for us all. Let's see. That cool average point. Meaning the first endpoint. Okay. Now, what do we have here? I'm going to go here in blue. I said in blue. So I know it's right above us, but I'm going to rewrite it here. H2A goes back and forth to make H plus and HA minus, and that has a Ka1. We also have HA minus back and forth to make H plus and A with a 2 minus with a Ka2. If I were to add these up, we would notice, Garrett, this is not true. You with me, Garrett? I'm going to try to draw it as lightly as possible. Right, they're still there, okay? But the overall equation would be H2A back and forth to make 2 H pluses and an A2 minus. That is governed by Ka1, Ka2. You guys all with me?
Mm-hmm.
Okay. Let's go ahead and write that equilibrium expression. So that equilibrium expression would be that we have Ka1, Ka2 is equal to the concentration of H plus squared. You guys hearing that yet? You hear the meltdown back there?
Barely.
Maybe we should bring him in here and make him stop melting down. Okay. Let me see something real quick. Hey, Hunter, you want to make your cameo? Too busy crying? Okay, well, you can't make his cameo. Oh, he wants his cameo now? That'll make him stop crying. Sorry, guys, I had to bribe this. Make him stop crying here. Come here. Come here. Can you guys see me?
Yeah, we can.
Can you see that?
Yeah.
Aw.
Hi.
That's all my students. Say hi, students.
Hi, students.
Wait, what's a wonderful teacher? You remember?
Pain is a wonderful teacher.
There it is. Payne is a wonderful teacher, teaching them well. All right, go back to mommy now. Thank you. All right, stop sharing that. All right. Payne is a wonderful teacher. Okay. Anyone who has kids, anything to make them stop losing their mind. All right. H plus squared, A2 minus over H2A. Why did I do this? Because I want to point something out. At the first endpoint, what can you tell me about the concentrations of species at the first endpoint?
All of the acid is gone?
All of the acid?
No, but I don't know.
No, Kimchi, that was you, right, Kimchi? Yeah. At the first endpoint, what have we done? The first H
Pluses are gone.
is gone. Yeah. Okay. So what does that mean? That means if my first H is gone, that means that half of my acid is gone, yes?
Yes.
That means that for every acid I generated, for every acid I killed, I also generated that much conjugate base, right? So the first H is gone. So half of the H2A is gone, generating the same amount of A2 minus. You guys with me? Now, if that's the case, then that means, therefore, oh man, I gotta zoom back in, that's bad. Therefore, at the first endpoint, the concentration of H2A is equal to the concentration of A2 minus, right? Half of our acid is gone, generating the same amount of the conjugate base. So those two are the same. What does that do to this equation then?
Cancels out.
Yeah. These guys would cancel out, right? So let me redo that down below so we can see it. So if that's the case, then Ka1 times Ka2 equaling the concentration of H plus squared times the concentration of A2 minus all over the concentration of H2A. Those two go away. So we are now left with Ka1, Ka2 is equal to the concentration of H plus squared. Logs. All right, we're going to take logs on both sides. And in fact, I'm going to go ahead and do that and say log of Ka1 plus log of Ka2, properties of logs, if I multiply and I can add them, is equal to 2 times the log of the H plus. Properties of log, I can take the power and put it in front. All right, I'm also going to go ahead and take the negative of everything. And the reason why I'm doing that is because a negative log means P, right? So that means P. So this now turns into pKa1 plus pKa2 is equal to 2pH. Which of course now pH equals pKa1 plus pKa2 all over 2. And that is why Ben's intuition was absolutely correct. Why not just figure that that is going to be the average of the pKa's? I kind of drew it in such a way that it would imply it as well, but heck, Mother Nature loves patterns, so why would it break now? Okay. How do you guys feel? You ready to try one? Yeah.
Yep, I think so.
All right. Kyra says it is true. Thank you, Kyra.
No problem.
All right, let's do one here. Ooh. Hey, Tanaris.
Yeah.
Yeah. Hey, is it better with my Zoom in and out? Am I doing okay?
Yeah, can you just scroll up for like 1 second?
Yeah. Why don't you chime in there and say, hey, can you scroll up, Pra?
Because if you didn't, I would have just got it from the notes later.
Yeah. You guys are supposed to help me make better notes than this.
All right, I'm good. Thank you.
You good now? Okay.
Yeah, thank you.
No, more than welcome. Thank you, sir. All right. Now, let us do one. Ooh. Let's look at phthalic acid. Oh, do I have another shape in here? Do I have? Oh, I don't have a hexagon. Rudica, where's my hexagon?
I don't know.
That's not very
Try
helpful.
to draw one and do the ink to shape. Just click the ink to shape and try to draw
Oh, yeah.
one.
All right. So I'm going to try this.
You have to click it first.
Wait, do I?
Yeah.
Or do I have to do this? Ink the shape. Oh, didn't like it.
You click it and it stays on. So as you draw, it tries to turn your
Oh,
stuff into actual
all right.
shapes.
Well, let's undo that. So ink to shape. I'll click it.
You're
still using the capture thing.
Everyone laugh at the prof. Oh, snap. Ooh. Actually, that's not true. Let me undo that. Stop it. All right, check this out. Come up here to a C, over to a double O, to an OH. Whoa, I'm still in ink to shape and it's trying to do my thing here. Coming up here to a C, double bond O, O, H. Actually, I should probably undo that and that. We'll just call it an OH. All right, so take a look at this guy. I think we have to do one there, and one there to fulfill our sets. Wait, at the endpoint 1, do we have half our H2A removed and an equal amount of A2A generated, or all of our? Oh, it's just half. I don't know who typed that, but that is awesome. Who just did that? Was that you, Dallas? That seems like a Dallas thing. Of course. Dallas, keep that up. What Dallas, I don't know if you guys saw, did you guys see that show up with this question?
Mm-hmm.
Oh, perfect. All right, so if anyone, use that little Blackboard thing, go ahead and type your little thing and put it in there. If you're too shy to speak or don't have a mic. Yeah, so that first endpoint, we've only removed half of the H2A and generated the exact same amount of A2 minus. That's why we're able to get rid of them.
Wait, so for when you remove half the H2A.
Sorry?
Yeah, hello.
Mm-hmm.
Is half the H2A left or is it HA now?
It is now HA.
Okay.
Right? Basically, if half of it's gone, we're basically all to HAs, and we don't have any more H's going on because the OHs killed them, right?
Mm-hmm.
All right. So now, grab a little more coffee because I can. All right. Now, by the way, this phthalic acid, You guys actually know what this is. You know what this is? AKA your good friend.
Dicarbolic acid.
No, it's vitamin D, right?
You guys remember KHP? Right, that was your potassium, hydrogen, phthalate. Look, KHP, we've done titrations with this left and right. So how do they make a KHP? This guy, they just put a K on it. Right? And then now it becomes a monoprotic acid. Now we're not going to do that. We're going to go ahead and leave it as the diprotic acid. We're going to stick our H back on there. And these are the two H's that are coming off to give us our acid here. So many of you might recall that when we talked about acetic acid, right, there's our CH3, CH2, OH. As you guys will soon learn in OChem, the alcohol group is an acid because it's this H that's going to come off, and that is why acetic acid is a monoprotic acid. These other H's over here, they're all part of the hydrocarbon chain. They don't do anything. So get rid of all that so we don't confuse it. I just like showing you guys where these H's can come from when I can, because a lot of times they go like, oh, H-benz, benzoic acid. What does that even look like? And what H is coming off, considering if you looked up its chemical composition, you'd see more H's. Here I happen to know phthalic acid, and those are the H's coming off. All right, so we're gonna go ahead and write this in a more general form. So we have H2P. Remember we said KHP, it's not phosphorus, we're gonna go for phthalate. That's gonna break up into H pluses and HP minuses, and Chad, that's gonna have a Ka1 equal to 1.3 times 10 to the minus 3. I think it was you that were asking about the 1 versus 2 or something like that, or am I misunderstanding? It was, I thought it was somebody asked about that one. We'll have the second one, HP minus, back and forth to make H pluses, and our P2 minuses. That's now a Ka2 equal to 3.9 times 10 to the negative 8.
The K values are given.
But of course, my friend.
Okay.
The Kas will be given. I wouldn't expect you to know those. I do want to point out for kimchi that we do have the two regions here. They are off by about 10,000. That is kind of typical for a lot of weak acids, and hence why we can see essentially an increase of just about 5 when we do our polyprotics. When we get into 3s, the Ks will start to blend over a little more. They'll be a little closer. They'll go like 3, 5, and 7 or something like that. So you won't see as big a separation as you might like. Phthalic acid is kind of nice because it does have that 5 orders of magnitude as a jump. So when we make this plot, we'll be able to see it pretty well.
Mm-hmm.
I do want to note as we begin, this Ka1 equals to 1.3 times 10 to the minus 3 is not very small, but let's pretend. Except Alice. Who's going to actually do the quadratic for us just to see it. Oh, that was an awful pretend. Come on. Call me out on my handwriting here. So let's pretend, except Dallas, to save us from quadratic. Okay, so what I want us to do is let's do one of these. I have the equation up there. We're going to go ahead and come back and refer to it. I'm going to see, have I been doing pretty good on my spacing? Not bad. Okay. I can go a little bit further out if I need. Okay, so how about this? We need a titration curve worthy of Mordor. So, draw a titration curve worthy of Mordor. Or, I should put 4 over here. You hear him in the background?
No.
Okay. It's kind of distracting, but I'm soldiering through. All right. 360. Let me write that better. 360 milliliters of 0.8 molar sodium hydroxide, titrating 100 mils of 1.2 molar H2P. Now I made it pretty concentrated to try to minimize that K issue. Okay, since we know we're going to go ahead and generate a curve, why don't I go ahead and, ooh, I think there's a way for me to insert a table. Oh my gosh. Can I do that? Nah, I'm not going to do that. All right, let's go back to draw. Let's go ahead and make our table up here. We need volume of the base versus the pH. Don't you remember? Yeah, it's his favorite song right now. Apparently, we built the city on rock and roll. Volume of NaOH and the pH that we're going to get. Now, in order to make this table, we do need to know where we are stopping, so we should probably get that first. Does anyone have an idea of where we might be stopping? Or how we would get that?
M1V1?
Yes. All right, first things first, we need to get that endpoint. So I'm going to go ahead and section this off here. So we're going to need that. So first, who's that?
It's Isa. Why do you have volume of NaOH and pH instead of base?
Why do I have the what?
Why do you have pH and not base, like you did with the other titrations?
Oh, I could just say base, but since I knew it, I decided to call it by its name. Doesn't matter.
Okay. Okay, thanks.
First things first. Where to end? All right, Kimchi just pointed out that this is going to be M1V1 equals M2V2. And so we have our 1.2 molar and 100 mils is equal to 0.8 molar. Oops, let's write that a little better. 0.8 molar. And the question is, how much do we need to actually neutralize this? If we divide that out, our V2 is going to be the 150. Deafening silence says my notes are correct. All right. Now, what is this telling us here then? If this is 150 mils to the end point, take a look at how much space I'm adding. What does that tell you? Low band, what does that tell you?
I'm sorry, repeat that.
If it only takes us 100 mils, take a look at what Dallas just wrote. If it takes us 150 mils to actually neutralize, but by the end we're doing 360, that tells me I've gone way too much.
So then do you do a smaller?
Nope, I said this is what you did. You were not paying attention in your titration and you just decided to go woohoo. So let's see what that looks like. If 150 mils gets us to the first endpoint, what does that now tell us? Immediately. Other things. This now tells us. Look at that. Can't silence Dallas no matter how much we try. That is correct, Dallas. So if 150 is to the first endpoint, then 300 mils is second endpoint. That also means that we know our other halfway points. That means that 75 mils is first halfway. And that also means that, what is that, 150, 225 is the second halfway. You know who we're missing now that I realize? Where's Lim? I told you guys to look around and tell me who was missing. I blame you. All right. So if those are our volumes, we should probably get over here and actually fill in our chart. So we clearly need to get to 300, and I would say we should probably get a couple 3 points past. So if 300 is our end, but we accidentally went 60 mils over, maybe we'll do 320, 340, and 360. What kind of intervals do you think you want to go if our halfway point is 75?
15.
15s would be pretty good, I would say. 25, I would probably not, I mean, you'd get the idea, but ideally we'd like to get a good 3 points on either side of each halfway point to make a decent curve. 25 would only give us 2 on either side, which is really kind of pushing, making a good looking curve. So we want to make sure we have enough points. You know, we could go 15, 30, 45, 60, 75, that's 4 on each side. And since they're pretty easy to do, why not just go ahead and do it? So let's see, we are going to have 0, 15, 30, 45, 60, 75. And then next is what now? 90, 105, 120, 135, 150. That's going to be 150, 65, 70, 180, 195. What is that now? 210? Is that right? And then 225. 30, 40, so that's 240, 255, 270, 285, and now 300. And finally, we'll go 320, 340, and 360. Now, I know that looks like an incredibly long chart, but remember, we can get a lot of these fairly quickly once we just plug into our Henderson-Hasselbalch situation.
Why did you go by 20s at the bottom?
I just chose. I knew that was going to come in, Chef. You can go as little as you want, but you'll clearly see very quickly that when we do this, I'm going to make a better zero here. When we do this, the endpoint volumes will very quickly jump that pH. So just sort of rounding out that curve. If you realized at the end, maybe you wanted one a little closer, and maybe we will make Dallas do like a 305 just for kicks as some secondary generation of points. Really, I would say just get enough to sketch a curve. Don't just jump to 360 and think that that's going to be good. That's really, this is about making a good looking curve, not about having the exact right answer.
So will we always go by 10 to 15 intervals on the test?
No, we just chose 15s because it would end up landing on our midpoints. In previous classes, we'd gone by 20s. We did 20, 40, 60, right? But, and then just plugged in the midpoint. Since Boudica said 15s, I just went with it. Why not? You could have gone 20, 40, 60. That would still be 3 points on either side. And your midpoint calculations would just be their own calculation anyway. So there is more than one way to do this. Okay. So as we have that, oh, I guess I should have done that in black. As we now have ooh, don't do that. No. What we can do now is get the easy points as quickly as possible. So now let's get the easy points. Fast and easy points. What are going to be the fast and easy ones that we can get?
Halfway.
Halfway, that's right. So the first halfway, we know that that's going to be pH equals pKa1. So pH equals negative log of, what is that? 1.3 to the negative 3. And that is equal to 2.89, I believe. And the other one we can get, Chef?
Our endpoint?
No, the other easy point.
Is it?
Oh, the second halfway?
There you go, second halfway. So you can see very quickly as we look at this, there are very easy ways to get some fast points and fast places to sort of pin down where our curve is going to go. So that's pH equals pKa2. So pH equals negative log now of 3.9 times 10 to the negative 8. And that is equal to 7.41. And finally, we have one more that is going to be pretty easy. And that is Johnson, what's that easy one going to be?
The first endpoint?
That's right. The first endpoint. Because we know that's going to be pKa1 plus pKa2 divided by 2. So that's going to be, oh, what just happened? get back here. That's going to be 2.89 plus 7.41 divided by 2, or that's going to be 5.15. So now we have at least 3 points on our curve. And that took us all of like a minute to do. Let's go ahead and put those in while we have them. So we'll come back over. So we have 5.15, and we had down here 7.41. We had, I think it was 2.89. Okay. Now let's get some of the, I wouldn't say more difficult, I would say the more time-consuming ones. Let's go ahead and get our initial and our endpoints, and then we'll just rip through some Henderson-Hasselbalch. Okay, so our initial point. As we pointed out at the beginning of this section, that's going to just come down to x squared over a minus x is equal to k a1. Ooh, what color did I use on that one? I think I used red. Oh, let's do red. So the initial point was x squared over a minus x is equal to k a1. And so that's x squared over 1.2 minus x is equal to 1.3 times 10 to the minus 3. Now, Ariana, you're going to go ahead and tell me to, oh, Ferris? Is Ferris here? Oh, all right. Anyway, between the two of them, neglect. Okay, thank you very much. Thanks for the enthusiasm there, Issa. All right, so we're going to neglect x. Neglect x and solve. By now, I think we're okay with this. And x is equal to 0.0395, which would now give us a pH equal to 1.40. Is everyone okay with that? Do I need to show the negative log thing?
Nope, I'm all good.
Okay. So now we have this guy. Whoa, don't do that. Now we have this guy. We can go ahead and put it up there real quick. Hey, Dallas, what did you get if you did your quadratic? And don't tell me you got all lazy on me when you know I was going to task you with doing it. Yes, we should, 388. So that's actually pretty good. That's actually only about 3% off, I think. So we're okay. So it turns out that even though we were pushing it, we're okay. What'd you get for your pH then, Dallas? Probably like 1.41 maybe, or 3.9, one of the ways. So the point here is, yeah, 141. You know, you would not be off enough to really matter. The fact of the matter is, when I did this problem, doing the same thing, it was 3.29% off of the total. And as long as you're within 5%, you're okay with this neglecting X. So that's why I kind of cheated at the beginning and said, we're just going to do it because I already knew the outcome. let's go ahead and do the final point then. Now the final point is that x squared now over b minus x, and this is going to be equal to kb2. Remember, we are now at the end point, but the second end point. So we got to make sure that we're talking about the correct k when we're doing this. We also need to figure out what b is. We're able to take a straight away because we're starting out with that concentration at that volume. We can just use it. But to get b, just to remind you, this b is all coming from the original acid generating the conjugate base. So get b. We're going to have 1.2 moles of the H2P per liter. We had 100 mils, so 0.100 liters of H2P. We know that it's 1 mole of H2P to every 1 mole of P2 minus. And now at the end of all this, our final volume is going to be that endpoint volume of 300 along with the 100 that we started. So that's 0.4 liters of solution, right? So that here is the 100 initial and the 300 added. That should give us 0.3. Now that we have our B, it's just math. We have now x squared over 0.3 minus x is equal to 3. Oh, actually, it's equal to the KB, but we don't have the KB. But we can get that. How do we get that?
Ka times Kb equals Kw.
Right, so we'll solve that with the 4K KB, so that's going to be Kw over Ka2, because we're looking at the second. So this is now x squared over 0.3 minus x is equal to 1 times 10 to the minus 14 divided by 3.9 times 10 to the minus 8. If we do the math, you end up that x is equal to 2.77 times 10 to the minus 4. And so, Ferris, what is x? And she will say the OH minus. Which means we have to solve for the H. I didn't actually do that, but we will end up with a pH equal to 10.44. Does anyone need me to solve for the H plus? Okay. Is that you, Dallas, writing no? I want to know who the chicken scratch is. That's kind of funny. So we can come up here and write 10.44. Okay. Now, let's plug some fast and easies. Look at one other thing. Okay, what is that other thing I have to look at? How do we get the points in between? What do we use?
Anderson-Hasselbalch.
That's right. So points in between. Was that you, Chef?
But
Okay. we know that we're going to use the HH. Now, you notice that I did two different regions, right, in the initial plot. Why do you think I broke it up into the two regions? Because while they will actually be, yes, use a different Ka. Why they will actually be using the same equation, they are governed by their own Kas. So hopefully it should be intuitive here that now I'll just say for region 1, it is going to be pH equals pKa 1 plus log of x over a minus x. If we're in region 1, we're talking about the Ka1, which means in region 2, it's Ka2. Okay, so now we need A and we need X. Need A and X, so A. That's that 1.2 moles of H2P per liter of H2P, and we had 0.1 liters of H2P, which means A is 0.12 moles of the acid. X. Now again, Chef, this is all about whatever your increment happened to be. If you wanted it to be slightly different, that is okay. Now we happen to choose 15. I do not have this number. So the X is going to be, I think it was 0.8 was our molarity. So 0.8 moles per liter. And we decided on a 15 mils or 0.015 liters. That's what, 40, is that 0.012?
0.012.
0.012 moles of base. Okay. So knowing that, we're just going to go ahead and plug that in. Oops. So at 15 mils, pH equals, we had pKa1, which was 2.89, I believe. Yes, 2.89. 2.89 plus log of x. And I'm going to go ahead and put that in a different color. Oh, watch this. Oops, no, not that. This. I'm going to put the base in red. Ooh. And I'm going to put my A in black. Let's do that. So log of our base, which is 0.012, all over 0.12 minus 0.012. Now, thank you very much, Dallas. I appreciate that because I don't have these numbers because we decided on this interval this time. So I'm going to go ahead and say at 30 mils, the pH is equal to 2.89 plus log . And this, so I think, Chef, this goes back to your question earlier, so I'm going to give it to you.
Well, wouldn't it just be 0.02?
That's right. Because we are just doubling the amount of base, we can just double the amount of moles there. That's totally fine. And Dallas will tell me that that's 2.28. And at this point, we can say ditto for first region.
I have a
Okay
question.
with that? Who's that?
Shauna. Just to clarify, we could be using this Henderson-Hasselbalch, we could be using that for the first initial easy points also, right?
Yes, yes. So some people, you know, just blast straight into, let's Henderson-Hasselbalch this. If you want to do that, go right ahead. In fact, well, the first thing you always have to do is to figure out your endpoint. Once you know your endpoint, then you can do whatever you want. Meaning you can jump to your midpoint and your first endpoint, or you could jump to the Henderson-Hasselbalch. Because once you know the endpoint and you also know the midpoint, notice that Boudica was very quick with her math and said, let's choose intervals of 15. She chose the intervals of 15 because it would end up landing on her midpoint of 75. Okay? Which means technically, if you, can I make a better 8 than that? If you were blowing through a Henderson-Hasselbalch, but made sure that you landed on your midpoint en route, you wouldn't have to do the pH equals pKa1 and pH equals pKa2. You could actually mow right over the top of it as you're doing your Henderson-Hasselbalch. When I did this last semester, last year, they chose 20 mil increments, which still gave you 3 points on either side. But that just meant that they would do one more calculation using pH equals pKa. None of it takes any less time overall. So it's just whichever one you're most comfortable doing. Does that make sense?
Yeah, thank you.
Okay. Okay, so I'm going to go ahead and zoom out, and I'm going to start writing these things in. And Dallas is going to start typing out, Dallas is going to start typing out all those numbers for me. So 15, 1.93, I think? Dallas, type away.
Which one are you asking about?
Oh, we already did 15 and 30, but I scrolled up, so I don't have them.
Oh, it's 1.94, 2.29.
1.94, 2.29.
9.
Then let's just keep going.
2.52.
2.52.
2.71.
2.71.
Skip, and then 3.07.
307.
3.26.
3.26.
3.49.
3.49.
3.84.
3.84. Now, just for kicks, since you clearly have this up, I think that's kimchi.
Mm-hmm.
Can you go ahead and type that in for the 150? Does it work?
No.
No. Remember, the Henderson-Hasselbalch does not work for your endpoints. Now, let's talk about this. Region 2. Let's talk about region 2. Underline region 1. I will now. All right. As you guys have already done the intuitive leap here, that is pH equals pKa2 plus log of x over a minus x. Okay. Do we want to make our lives hard or easy? Tanaris.
Yes.
Do you want it hard or easy? I know you want to make it difficult, Dallas, but I don't.
Well, hard.
Wow, why did somebody all of them make it hard? I'm going to make it easy. Take a
Okay.
look. I'm going to scroll back. I'm going to scroll back up here. And I want to go to, oh, let's go to the very beginning here where I had my thing. All right, region 1 and region 2. Region 1's Henderson-Hasselbalch was governed by a pKa1, and region 2 is governed by a pKa2. All right, and in fact, we can go ahead and write those up, that in this area, this is pH equals pKa1 plus log of x over a minus x. And over here, pH is equal to pKa2 plus log of x, of x over a minus x. Now, if my base increment were 15 mils through region 1, and I'm going to go ahead and keep that through region 2. If you decided to try to make this really weird, you could, but you can always fall back on the idea that the whole time that we are neutralizing, how many H's are we neutralizing at any given time? 1. Okay, we spent this whole time saying, look, we get to do N1V1 because as we are doing these acids, we are doing 1H for 1 OH no matter what. So if we were in the classroom, at this point, I would cover up the left-hand side, covering up region 1, and say region 2, let's do the Henderson-Hasselbalch. And so let's choose RA. And we would determine RA exactly the same way that we did the original one. And we determine Rx exactly the same way as we determined the original X. And the reason we're allowed to do that is because we are now just concerned about getting rid of that H for that region. And as I stated at the beginning of this, it looks like I drew essentially the same monoprotic acid curve and I just raised it up a little bit. And that is exactly right. They will behave exactly the same way. The only difference is the scaling factor. And that pKa2 is going to be our scaling factor to accommodate for the fact that we're in the new region. So what is the end result of this? That means that as we get down here to region 2, our A and X values remain the same. The pK, ooh, come on, don't get too excited. The pKa2 is our scaling factor to represent our new equilibrium region. And so, what's our first volume? 150 is what? 165 is our new volume. So at 165 mils, he says each endpoint equals corresponding region 1. Each point equals, oh man, Dallas, I wish you had a mic. I don't understand that question. Dallas, go get a mic.
I think what he's trying to say is that you just add the difference between the pKa's.
I'm going to say probably, and we'll see if that falls out. I always hate the absolutes unless I've actually gone ahead and done that. I've never actually said, oh, I'll just take those and add the pKa2 amount difference. So if that does seem to work out, Dallas, then it actually wouldn't surprise me because we have set this interval to be the same. My brain is quickly doing all the calculations. Yeah, you might just be adding the difference between pKa1 and pKa2 because it is just the scaling factor. But let me just do it my old school way of the long way and see if this works. So 165 mils, we are 15 mils into region 2. So that means that my pH is equal to pKa2, which is 7.41. And since we are going in only 15 mils into region 2, we can go back to that increment, I'm going to remind us, which is 0.012 moles into region 2. So we get to go back and say 0.012 all over the acid, which we're still neutralizing, which is 0.12 minus 0.012. Dallas, give it to me. Yeah, actually, Dallas, your intuition is right on that, I think. We can take the original pHs and just add in the difference. Dallas, where's your blue text type? Or anyone else who's already got it. Oh, cool, working on it.
6.45.
6.45. And let me just point out that 70, 80. So at 180 mils, we are 30 mils into region 2. So that means our pH is equal to 7.41 plus, get this where my hand won't budge, log of, and Chef will tell me just double it, so 0.24 over 0.12 minus 0.024. We get to do this because our pKa2 is taking care of that. And got the same thing by adding the differences in the pKa's. Yeah. You know, like I said, as I was doing the clever math there in my brain there, Dallas, yeah, since this is just a scaling factor to get us into region 2, and because we're choosing such beautiful systematic and sequential points, it does not surprise me that does, because it is just a scaling factor to do it. Before I started just making beautiful titration curves, I used to be really mean to students and say, give me the pH at this point and that point and that point. And they were all like randomized. So you'd have to do all these calculations over and over again. And then one day I woke up and was like, oh, why not just generate a beautiful curve and find your spot on that curve? There's no point in randomizing these points, because it's actually more efficient to just make this happen. So what is that pH?
6.81.
6.81. Okay, so at this point, I'm going to say ditto for rest of region 2. And we're going to go ahead and go back up and input those in, because I'm sure Dallas has generated them all, or Chef has. So I already forgot. 165 was
6.45.
645, and I think you said 682.
681, yeah.
681. And then we had
704.
And then we got to be in the 2s.
7.23.
Okay, then 741, then probably in the sixes.
Oh, my calculator died. Sorry.
All right. Dallas, you have them all up. $7.41, then seriously, let's get a GoFundMe so Dallas can have a mic. I miss his dulcet tones. 7.58. And where's my other calculator, Mr. Lim? I blame him for abandoning us. So 75 maybe, somewhere around there. Maybe 74. Oh, 77, sorry. I didn't, it was underneath my hand thing. The next one is who else is around here still? Did people like drop out? They're just like watching? Bueller. Oh, it's already up to 801. Okay. And finally, 8.36, you say? Okay. All right, we're almost done with this problem. We just need to get to our over titration parts. So let's get to the over titration. Over titration. Okay, now, as we said last time in the over titration, at this point, we are governed completely by the addition of the OHs. Right at the end point, when we've gotten rid of all the H's and OHs, finally the conjugate base can do its job. It's its turn to shine, but they basically get one shot at it. Then we put in the first string quarterback and they take over. So let's take a look at 20 mils over. Okay, we had, let's see, do I even have that in there? Hold on. Where'd it go? I don't have it. So we'll have to just sort of do it on our own here. All right, so 20 mils over. What was our base? It was 0.8?
Yeah.
Okay. So we have 0.8 moles of sodium hydroxide per liter of sodium hydroxide. And we'll do 0.020 liters of sodium hydroxide. We know that 1 mole of sodium hydroxide gives you 1 mole of OH minus, but now we need the total volume of the solution. And hopefully you guys realize it's 0.420 liters of solution. And again, that's the 100 mils initial plus the 300 mils to the end plus the 20 mils over. Now if you plug and chug that, you'll find out you get 0.0238 molarity for OH minus. Which means at the end of all that, I don't have to do all this for you. What's the pH at that? Oh, you said, oh, 381, not 281. sorry. And what's the pH on that then? Probably got to be in the 12s.
It's 12.58.
12.58. Now, at 40 mils, are we okay just saying ditto, ditto, ditto? Oh, no, it's actually going to be not ditto or ditto. We can't do that, sorry. Unless we can do a ditto till the end, I might as well just do the whole thing. So that's 0.8 moles of sodium hydroxide per liter of sodium hydroxide. Now we have 0.04 liters of sodium hydroxide. We know it's 1 mole of OH minus over 1 mole of sodium hydroxide. And that's now 0.44 liters of solution. We keep adding in the 20 mils. 0.0727 is what Dallas says. It's funny, every time you type, you end up underneath my little hand pad that I'm using to make sure I don't register this with my hand. So at the end of that, that means we're going to be at a 12 point, I bet we're in the low 6s.
12.86.
86, sorry. Okay. And then finally, at 60 mils. So 0.8 moles of NaOH per liter of NaOH. I mean, I guess you could say ditto and for the beginning and the 1 mole of 1 mole, if you guys really wanted. 0.60 liters of sodium hydroxide. You could even, if you really wanted to, just show one of these and probably plug and chug. Just remember, it's 0.460 liters of solution. He says it's 0.1043. Which means our pH here is, ooh, are we gonna actually bust into the 13s?
Yeah.
13.02.
02.
Okay, so then we're almost done with this long lecture of longness. I apologize to everyone who's not here who has to watch this. All right, we just said that was 13.02. We had a 12.86 and a 12.5 something.
12.58.
58. Okay. Whew. We are almost done. Now we just have to plot it. And because I'm silly, I forgot to do my graph thing right near where I was going to need it. So, oops, undo. I wanted that in black. Okay. So now we need to actually get our scales going on here. So here we have our pH and our volume of phase. So I'm going to go ahead and give a mark here and a mark here. We know that our first endpoint, oh, actually, Let me take that back because we need some points after it. So I'm gonna put a point here, and a point here. We knew we were at 150, 300. There were 75 and 225. And so if those are 75, 60, 45, 30, 15. Okay. We started pretty low. What was our initial again? In the ones? I'll just go 1, 2. It's probably 1 point. Yeah, I think it was 1.93 sounds right. So let's see how far I can space these things out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oof. Okay. Now, if I can do this cool, I can do big fat ones there. So our initial point was 1.93. And then we jumped up to, somebody go ahead and call them out for me. Good.
Wait, I think our initial is 1.4, I thought.
Yeah.
Oh, is it 1.4? Okay. Oh, okay. Somebody typed in 1.93. Ah, mis gatos. How do I get rid of the dot? Oh, there we go.
The back.
1.4 you said?
Yeah, 1.4.
Okay. Next one.
1.93.
Okay.
2.28.
Check.
2.52.
Check.
2.71.
Check.
2.9.
Okay.
3.1.
Got it.
3.3.
Okay.
4.5.
3.5.
Oh yeah, sorry, 3.5.
Okay.
3.8.
Okay.
Sorry.
That's 4. Was it 427 or something like that? First endpoint was
5.15.
Was it really 5? Oh dang. Oh yeah, 515. Yeah. Okay. And after that,
6.45.
oh yeah, 6.45. Okay, then
6.81.
then
7.04.
then
7.23.
and
7.41.
okay.
7.59.
Okay.
7.78.
All right.
8.01.
And then
8.36.
and then
10.44.
10.44. Wow, I got to get up there. 10.44. All right, and then we said after that, we had things in the 12s to 13s, right?
Mm-hmm.
So we had something that went like bam, bam, and bam. So I'm going to go ahead and get those in those colors. Boom, bam, bam, and bam, something like that. I'm going to go ahead and note our midpoints. I think we're here and here. And our endpoint was the red one, and the red one, and of course, our initial one. So just sort of pointing out that as we do this, and then we go ahead and try to sketch through this, we immediately jump up, and then we run through this nice buffer region that pretty much is kind of flat and not doing anything. And then we get to this beautiful inflection point, and then we quickly jump into the other region, and then we get to another inflection point, and then we just start asymptotically tapering off. We'll never actually reach the pH of the base that we're adding because we're always diluting it, but we will asymptotically approach it if we just continue to do so. We don't need to because we're done with the titration. So as we look at that, that looks remarkably similar to the one that I drew at the beginning of this lecture when talking about the polyprotics. And actually not a half-bed curve overall. I think we did pretty well. I like that interval. Oh man. Hey, we should do a 3-1. Let's do it right now. Deafening silence means yes.
No.
I'm just kidding. We're not going to. It's getting pretty late. Let's see. I did put, I'm going to go ahead and stop the lecture here. But I'll stay on real quick. Stop sharing. And I'm going to stop recording.